Nadav, who will tell us about reWarding defects.
Yes, so thank you to the organizers for inviting me. It's my third time, I believe, at IGST, but it's a special honor to be invited to this very prestigious university to speak here. And I will be talking about work in progress with my ex-PhD student Ziwen and my colleague here, Petra Kravchuk. And as you already heard before, there is overlap with the talk of Barak and his collaborators. I'm stupidly an optimist, so I will tell you about unpublished results, even though we were scooped. I hope nobody will decide to publish what they see in the slides before me, and especially you. For diversity purposes, I also have my title in Japanese, and just for this context, this is the Integrability and Gauge and String Theory conference. My talk will not be integrability, not about gauge theory, not about string theory. It will be valid for any arbitrary theory, but it can include also integrable theories. Now, in every one of these talks, we start by talking, so this is about defects, and as Barak did, we start with our favorite examples of defects, and then, as you all know, we specialize to have BPS Wilson lines and n equals 4 super mills, except for today. Everything I'm talking about today is valid for absolutely every defect. You don't need supersymmetry, you don't need integrability. It can be a cosmic string as far as I'm concerned. And the defects break part of your space-time symmetry. So I assume that there is some space-time symmetry and possibly other global symmetry, and there could be supersymmetry if you want. And the defect will break some of them, and that was what is important. And just for notation, my defect will be p-dimensional and space-time will be d-dimensional. And as I said, if your defects are integrable, that is, don't feel bad. It works for them too. So, every quantum field theory should have an energy momentum tensor. If you have a global symmetry, then you also have a current for it. If you have a supersymmetry, you will have a supercurrent. And they have very important correlation functions among themselves that capture things like central charges. In the case that you have defects, there are contact terms for these operators on the defects. So the conservation equation for the energy momentum tensor will get a contact term restricted to the defect in p dimensions. And the operator that it induces on the defect is what we call the displacement. For a flavor current, the operator we call the tilt. And if you want, you can give a name tiltino to the one for the supersymmetry, or displacementino. I will not talk about supersymmetry much. So these are operators that live on the defect, and again, some people are somehow fixated. So as an example, some people are fixated with Wilson loops in n equals 4 super Young mills. So for their benefit, here is that Wilson loop, the Maldacena Wilson loop, and the displacement take this explicit form, so it's a field strength plus something else, or one of the 5 other scalars that is not one of the scalar that is inserted in here. So these are the explicit operators. If you like this theory, this would be the example I am talking about. But you can also look at a non-integrable theory like the one Julia mentioned before, the Owen model, and say take the magnetic line, or you can take a surface defect or anything in that model. But for the magnetic line, it has this form. Phi is just a scalar. So you'd integrate the scalar, but there is no gauge invariance or something. So you just integrate the scalar, and then the displacement is W times the derivative of the scalar, and the tilt is just the other n-1 scalars that did not appear in your defect. And another definition is that you vary the defect W, so I still keep the name out of sentiment. You vary your defect with respect to its position in the transverse direction or with respect to its location in this internal space of couplings. And this is a formal definition of what the displacement and tilt are. And the question I want to answer are, what are the consequences of the broken global symmetry on the defects? And they are going to be captured by correlation functions involving tilts and displacements. So here is the outline of my talk. You can look whether your favorite theory is mentioned here and when, and then you will know when to stop tick-tocking and start listening. So let's start with the simplest trivial identity. I copied these equations from before, and now we can integrate the energy momentum tensor to get a charge, for example, translation, P. And if you act with P on your defect, you will get an insertion of this, but because you're integrated, this insertion is integrated over the defect. And because of this delta function, it's only on the defect. And likewise with the tilts. So, and because this is a Ward identity, the right-hand side should be 0 for now. So for any defect, if you insert a displacement and integrate, you get 0. And this is completely general, and it's a very trivial identity. In a way, it appeared already in this paper, and as Barak was also mentioning, in the context of bulk defect correlators, but this applies very generally. So this was for translations. If you have rotation symmetry, as we usually do before we put the defect, or if you have conformal symmetry, you will get this identity with other weights associated to the killing vector of this, or the conformal killing vector of that. So as examples, take as your starting point a defect with already 2 insertions in it. It doesn't matter what your defect is, I said. It doesn't need to be conformal. It doesn't need to be anything. It doesn't need to be a straight line. I will take it to be a straight line, say, with 2 extra insertions. What you get is that the integral of this defect with 3 insertions, when one of them is the displacement, has to be 0. And likewise with the tilt, and here I took 2, and here I took 3. It doesn't matter. So let's make it explicit and show you an application. So here I start with 3 tilts, correlation function of 3 tilts. I act with a global symmetry. I will get an integrated correlation function of 4 tilts, and that better be 0. Now, in this theory, 3-dimensional n equals 4 Chern-Simons matter theories, there are many such theories, and these people determined what would be the form of the correlation function, the 4-point functions of these tilt operators at strong coupling. And they found an answer that depends on 2 parameters that I call here eta and epsilon, changing a little bit their parameter. The tilts there, they have 2 that I write here as complex conjugates of each other. And so I take this relation, and I just integrate this function that they tell me is the answer. So they have a bunch of conditions that they wanted to impose, that they decompose into superconformal blocks, and so on. And you integrate it, and you find 8 pi squared eta, and that is equal to 0. So either 8 is 0, or pi is 0, or eta is 0. Let's go with the last option. And then you get that the answer is just what's written on the second line, which is the same answer as an ABJM. So when this was done in ABJM, there wasn't this extra parameter. They thought that they found an extra parameter, but actually there isn't any extra freedom. And I should say, I don't mean any bad for them. They didn't know about this identity. What they did is correct. I believe we just added something that they didn't know at the time of writing their paper. So the answer for N equal 4 theories and for ABJM is the same. Let me look at another case. So I start with 2 displacements and I add a third displacement that still should be 0. I told you if I integrate on one of the displacements. And now let me restrict to a CFT. In a CFT, the form of the 3-point function is completely determined. The dimension of the displacement is always 1 plus the dimension of the defect. So the 3-point function better be this way. And now I'm instructed to integrate this. And the integral of this, you would tell me, is going to be proportional to C. If I integrate over anything, because there is just a number here, they're a function. But you should actually be careful when you integrate anything that you need to know it also at coincident points, and at coincident points you may get delta functions. So here I'm brushing over it, and I'm telling you that actually the answer, the delta function cannot cure this, and the right-hand side really is non-zero. And there is an anomaly that Chris and collaborators found for boundaries and interfaces. It's related to the extrinsic curvature. And so the conclusion is that this equation that I told you about is wrong. And there is actually a right-hand side to it, which may be an anomaly. So all these equations, you need to analyze whether there are anomalies to them. And this is part of the reason that our paper is delayed, because we don't want to write only the naive equations. We want to include all possible anomalies in them. Let me give you another example. So take a tilt 3-point function and integrate one of them. And tilts have the dimension of the defect. So the 3-point function of tilts will have the usual form in a CFT, plus a possible contact term. And now I'm going to be completely honest. So if you integrate this, if I integrate tau 1, then in the vicinity of tau 2, I have here 1 over tau 1, 2, small distance to the power p. I integrate it over p dimensions. I'm going to get a log. And this log indicates that, that something is wrong with conformal theory. And this is how you would calculate the anomalous dimension of the tilt in conformal perturbation theory. So, but tilts are really exactly marginal operator. This is precise everywhere on the defect conformal manifold. So the conclusion is that D is equal to 0. And no contact term will help you eliminate this log. So that is absolutely true, except for one case where you have one-dimensional defects, and you're allowed this form in addition to this form. So here you have this taus that can change sign, and you have this symbol which has to be completely anti-symmetric. And that is an allowed, as far as we know, this has never been written, that this is an allowed form of marginal operators in oriented theory in 1 dimensions. And again, the right-hand, now you have again a contact term, but that still doesn't help you, and the right-hand side is not 0. And this example that Barak talked about in his talk, this paper that studied this model both via Bootstrap and via ADS-CFT, they actually calculated 3-point functions of tilts and 3-point functions of displacement and found that they are non-zero. This is not surprising because of the anomaly. This is a little bit more surprising because nobody knew that such 3-point functions are allowed. But they are allowed, but they are related to some anomaly. And then you try to calculate an anomaly polynomial to add to your effective action. And it turns out that when you solve the Wess-Zumino consistency condition, to all orders in the deformation of the, so W I take here to be a deformation of my line. So I try to think, I start with a straight line, but I deform it in any arbitrary way, and this is the allowed form to get, except that this is not good because this is singular at pi. And this actually indicates that this form should not really think of it as this way, and I should think about it as some kind of topological condition So this defect is actually not a function of its position in this internal space, but it's some section of a bundle, and there is a global anomaly which has this cohomology of the loop group of SU2 with values and so on. Some slightly sophisticated math, but doesn't matter. And then you can calculate the cohomology, and you find an integrability condition that these parameters that appeared here that are somehow related to the number of brains that induce this background is related to these integers with this fraction of pi. And we checked, and these numbers, as far as we see, satisfy this integral condition. The number of d brains exactly appears with this power of pi, so string theory seems to be correct. So this is the flux quantization condition in string theory. So this is all I wanted to say about these trivial identities, and now I'm going to go to, which we still find nice results from them, and now I'll go to the more sophisticated identities, which also appeared in Barak's talk. So here you should think of me having two special operators arising from broken symmetries, any of the symmetries that are broken, and two other generic operators that can also be those, but can also be other ones. And the form of the identity is that I have a log, I have some polynomial of the cross ratios. Here I wrote it for two cross ratios, so generic, but it also works for dimension 1. And the right-hand side, you should think about it as having the commutator of these two charges that gave rise to these acting on one of these operators, and you get this two-point function. This two-point function of these changed operators. And this is the identity, and it's true for any of the broken symmetries. It's interesting only if they don't commute. And this gives you a relation between 4-point functions and 2-point functions. So here is an example in a 6-dimensional 2,0 theory where there are surface operators. And this already appeared in my paper from a few years ago. And these people, including me, calculated the 4-point functions of tilts using IGST25, and we found these 4 tensor structures, including this anti-symmetric one, and these d functions. And if you know what they are, that's good. And if you don't know what they are, you're better for it. And now you need to evaluate the integral, and you can just do the integral, and you find this structure, and this structure exactly is consistent with this commutator structure. It also is related to the curvature on S4, so it all works out very nicely. And then you can also do the same relation for other symmetries, the translations, rotations, and special conformal transformations. So in the same paper, we calculated the 4-point functions of the displacement, and you can look at it there, and it's just other different d functions, and you plug it into the equation, and it doesn't work because we had a typo, and then we're going to fix the typo, and then it's going to work. And then there is the other term, the last one term, which is this epsilon tensor, and that is again anti-symmetric, similar to the expression we had for the tilts in the 3-point function in the 2-dimensional theory, the IGST3 theory, and now it's related to some other cohomology. And this cohomology is also in the integers, and this is related to this coefficient of G, the number appearing here, 9 over 2n, is related to the form from flux on S4, and that is quantized, and that is quantized correctly, so M theory works as well, if you're worried. So how much time do I have? 10 minutes. Okay, plenty of time to go through the derivation. And the point of the derivation is that, well, the difficulty really is that everything here was defined to linear order. We defined the displacements and tilts by variating with respect to how far we move our line from being straight. And in order to go to higher orders in it, there are a bunch of ambiguities that are related to each other. You need to choose coordinates beyond linear order. You need to think of what is the second functional derivative at the same point, which is subtle. You need to act with a broken symmetry on a tilt or on the displacement, and that action is not well defined. Or you need to think of multiple OPEs of the same operators, which is again not uniquely defined. So you have a bunch of ambiguities, and you can choose a scheme to work very carefully in that scheme in one coordinate system, one choice of OPEs, and so on. But what we chose instead is to work in a completely agnostic way, in a scheme-independent way. And here I have a version of this trivial identity. I just integrate over 1 tau 1 with a trivial measure, and that should be 0. But I added here every possible contact term when 2 points meet each other. In principle, you can also add higher contact terms where more points meet each other. And these things I pick up when this tau 1 hits these other points. I get an extra term. So actually, they arise from triple delta functions. And I get these extra terms. And all of these things are ambiguous and undefined. And I try to calculate them and find constraints among them. Or if I want, I can calculate them in any particular scheme where I define all these ambiguities that I have here. And in order to get this L2, which appears in this identity, I actually have to start at a lower order, starting with my defect, which is parameterized by this W profile, either in space-time or for the tilts, and act with a global symmetry e to the lambda. Lambda is a generator of my symmetry group that is broken, and I find a vector field associated to it. I work only to linear order in lambda, arbitrary order in W, and I find some relations between this W. This is the correct equation where this vector field acting on my partition function, on my observable, will be given by some anomaly. And I need to analyze all these terms, all these possible terms, and find all possibilities. Let me skip this slide, which tells you how to get L0 and L1, which it's pretty straightforward to find them in any reasonable scheme. You can also go to crazy schemes, but we don't do that. And then you find this condition on L2, that it's related to L1s, and L1s are determined. So this combination of L2s is actually scheme independent. So L2 itself is scheme dependent, but we find that a particular combination of it is scheme independent, and any time we can extract this term, we're good. So I remember as a young PhD student, you were always told that symmetries are important and they're the base, and we try to base everything on that, and global symmetries and gauge symmetries and so on. And I felt that what a waste that that I'm not there when these things are discovered and all these symmetries are now very well understood. But I think that this is a case where we actually can say something new about how global symmetries act on a QFT. So I'm very excited about this. So just what we thought we knew about symmetries, they actually have very non-trivial identities when you have these defects that break global symmetries. And as I outlined, but I didn't say here, we have a very rigorous definition. We have to keep track of all contact terms, because when you integrate and you don't know what your delta function contributions are, it's meaningless. So you have to know what all correlation functions are as distributions, including all delta functions. And this is what is taking us time. And there are too many variations of these identities with all kinds of subtleties, and we haven't settled on a finite set yet that we want to publish in our first paper. But we will also have many of these plug-in formulas that you can take and apply to your favorite defect and check that your calculation is correct, or fix it, or fix extra parameters that are left free, like this eta that I illustrated at the beginning. So I could finish here, but a talk at IGST is never complete unless you talk about n equals 4 super-Young Mills or show these slides. Or make fun of the main organizer. It's here, your phone is here. So these are the results from this paper of these distinguished colleagues. And this is another application of the integral identity. I should say that they found the integral identity completely independently of my student and I by just looking at the correlation functions and understanding it and seeing that they satisfy this identity. And they found another identity which is very particular to n equals 4. So it doesn't fall under this category. And as they showed in their paper from a few years ago, this is extremely powerful in the numerical bootstrap, including these integrated constraints. So this is another application of it. Then in a more recent paper, they looked at mixed correlators, and there for some reason they didn't guess the integral identities, and they didn't read my paper with my PhD student, Jake, who's up there. And then they would have known that there are integrated identities for mixed correlators as well, two arbitrary spin operators. As long as you have two tilts in them, you have the same kind of identities. And then a bunch of people calculated 4-point functions in n equals 4 super-Young Mills at strong coupling, at large charge, all kinds of limits. Here is a subset of the authors. I don't like to shame people for having mistakes unless those people are Nikolai and or me. And we couldn't find any mistake in those papers. So even not, so Arkady, the reason for the mistake in our paper must be me. So so everything works just perfectly with the tilts or with the displacements. So Barak had a slide where he flashed through this and said that everything works, and I do the same, except when you go to weak coupling, and there is a result from that same paper of people at some university. I don't know where they were at that time, where they look at this 4-point function at weak coupling and try to implement some version of this integral identity. And the prescription they tell you is to take the answer, include an extra term, and then take all logs and set them to 0. And this is not the way we teach QFT around here. And as far as I know, in QFT, you don't set log epsilon to 0. That's actually where the meat is. And the same issue arises also in the ON model when you do it in perturbation theory. And the resolution of this is that you need to include a contact term and treat the correlator as a distribution. And if you do that correctly, the log divergence goes away. And so despite their best effort, n equals 4 is still a correct theory. And it's well defined. And you don't need to do weird things like that. I should say there is a logic to it. But the reason you could control it here is that you exactly know what is the offending operator and so on. And in other theories, you're not going to have this level of control, so you cannot really. It's a weak coupling feature, and it's a feature of all weakly coupled theories. It's a feature also of the ON model. But it's not, there is a way to do it legally, and when our paper is out, you will see that. So to conclude, there are many, many more examples to work out, and I'm working with Ziwen and Peter on it full time. But if you want to get involved and are interested in this, then talk to Peter or Ziwen and me, or you can hire Peter or me, but it will be much cheaper to hire Ziwen, who is applying for postdocs next year and soon for faculty jobs, and she is really the driving force behind this project. She was pushing it from the beginning and convincing us to work on it. Thank you. Thank you.
Question.
So in your earlier examples, you said that the contact terms won't save you, and so these coefficients must be 0. Can you also conclude then that there are no contact terms as well, or?
Oh, so in some, usually contact terms are ambiguous, and you can include them or you cannot include them, and there is nothing that that predetermines them. So you can just add contact terms to your correlation function. It will satisfy all the axioms of the CFT. We find, through these relations, you find constraints on the contact terms. So sometimes you will find that they have to be 0. Sometimes you find that they cannot be 0. Sometimes you find, as in this formula that I really flashed, and I don't expect you to have absorbed. So here we have contact terms, and we have these L2 terms, and I told you that they are scheme dependent, but there are combinations of them that are scheme independent. So here you have contact terms that are partially fixed and partially ambiguous. So, and this is the general rule, and I went way too quickly over this. This whole thing deserves a whole course, not a lecture, but that's what I have. We can talk about particular examples if you have any in mind.
So there's a result for a 4-point functional displacement operator in n equal 2 theories that depends on a free parameter as much as in the n equal 4 Chern-Simons.
That's right.
Set that to 0 as well? And well, and a related question is whether you have some holographic understanding of why that result in n equal 4 Chern-Simons equals the ABJM one.
So we have no holographic understanding, and this should be true for any theory. So I don't know all holographic duals of all n equals 4 theories. As far as the n equal 2 calculation, we are aware of it, and we haven't completed it. The form of the expression makes it a little bit harder for us to analyze, so we haven't completed it, and I don't know if we're going to do it in our first paper or not, but we're aware of it.
Are there other questions? I have one. So in the derivation of one of the identities, so the question is, can you determine the full, all the terms in the relevant perturbation theory, all the couplings to all possible operators? Or do they have a simple, for example, we had a sum rule at some point, and we eliminated all these unknown couplings with another identity. Is there a way to really fix all of them?
I think it depends on a case-by-case basis, and I haven't looked at that particular part of your paper in great detail to say exactly that. As Barak already said, in the case of n equals 4, all the identities reduce to the same one as the identity for the tilt. In a surprising twist, for example, in ABJM, this is not the case. Even though ABJM has a lot of supersymmetry, one of the displacement identities is independent of the tilt identities. You can't get it by integrating by parts. it's still satisfied. And it's satisfied by the n equals 4 identity. Of course, the n equals 4, I wrote the expression for the tilt. You can do the same with the displacement. You're going to get the same. So all of them are satisfied once you set eta to 0. But whether these are independent or new or so on, it's actually better to work in a theory with no supersymmetry or a small amount of supersymmetry, then you have more identities.
Maybe you have already explained, but about the log epsilon term, you say the contact term can allow you to set it to 0 about the final slide.
Yeah.
How does it work?
How does it work? No, I didn't explain it. What I said was that here you get this integral that diverges. And actually, what you get is that the integral identity is not satisfied unless you add this extra term. And the way I would say it now is that there is another way to add this term in a way that will make this integral explicitly finite to begin with. So there is no log, there is no extra term to add. You just redefine things in a way that you define the correlation function as a distribution. So you know the value away from coincident points. You need to add contact terms, delta functions at coincident points. You need to treat it as a distribution such that in the way mathematicians define a distribution as integral against test functions and so on. And then for every test function, smooth enough and so on, you're not going to get any logarithmic divergences.
A different way to do this.
Sorry?
It's a different way to do this integral.
It's a different way to do this that is completely honest and has no ambiguities.
Thank you.
Another way of doing that is take G finite and take the limit and do
That's right. If you can do a calculation at finite G, but again, in the ON model, you may not be able to do this.
Because this is equivalent to the Maldacena prescription for the Brent-Strahlung. Like he's putting a regulator, and then he's saying like there is 1 over epsilon. Who cares? So this is 0.
It's not a log epsilon. It's a 1 over epsilon.
Yeah, but it's a. I mean, like his power like it is log epsilon, but it's equivalent.
Oh no.
Come on, you can say like.
Oh no, we know that this is exactly the kind of thing that I don't want to be taught at King's College. Okay.
We're in Bush House.
Yeah,
Bush House has different rules. Yeah.
So it's fine.
This is not how QFT works, sorry. You don't cancel one log epsilon against another log epsilon.
G.
No, at finite G that is perfectly fine. Finite epsilon, that makes no sense. But you can't do calculations at finite epsilon in ON.
Sorry, I'm talking about finite G, yes. Okay, finite.
Okay. If you can do a calculation at finite G, there is no issue with the divergences. This formula is not at finite G. This is a perturbative formula. It's correct, don't worry. Makes no sense, but it's correct.
Other questions?
It's just minor things we're cleaning up, don't worry.
Okay, if not, then it's time for the coffee break. Let's thank Nadav again.